Our first presentation in this newly initiated cost estimation track is cost considerations for estimating small satellite integration and test by Rachel Sholder and Kathy Koff. So Rachel is a parametric cost analyst within the systems engineering group at APL. She joined APL in 2017 after graduating with MS in statistics and BS in math. Rachel has since become a valuable team member responsible for lifecycle cost mission estimates at various stages of programmatic development. Rachel was named the NASA Cost and Schedule Rising Star in 2023, and she is currently working toward a doctorate with a focus in applied math and statistics. Kathy is a parametric cost analyst within the systems engineering group at APL as well. She is responsible for lifecycle space mission cost estimates at various stages of the programmatic development as well. She has a bachelor's degree in applied math from University of California, San Diego, and a master's degree from USC with a doctorate from Johns Hopkins. Please welcome Rachel and Kathy.
Good morning, everyone. Okay, so get started. So the way that this research came about, so we work in the civil space area at APL. And within that area, we do a lot of the pre-formulation proposal work. And we were noticing that we were starting to do a lot more small satellite CubeSat type proposals. So with that, we needed a better way to estimate the various WBS elements while we were formulating these concepts. And typically the approaches that are used are, the wrap factor approach, analogies to similar missions, and a bottom-up estimate. That last one takes a lot of effort. So, not something that usually is done that early on when we're still trying to figure out what we're doing. And so the wrap factor approach and the analogy approach are the ones we typically lean on. However, for these small satellites, we didn't really have a lot of analogies to pull on either. So that leads us to the wrap factor approach. So this involves estimating mission INT or system INT costs as a percentage of your payload and your spacecraft hardware costs. This is all based on historical missions with the assumption that the project being estimated shares similar characteristics with the data set that you developed your wrap factor with. However, for these small sats, they obviously didn't share very similar characteristics with a lot of the larger, Class B, Class C missions that we were doing at APL. So that technique worked great for traditional builds, but with the CubeSats, the underlying cost basis was just not large enough to generate a high enough INT cost using that approach. So this suggests that there is a floor to INT costs. So there's like a bare minimum of how much INT will cost as a baseline for just the labor and testing you have to do to get started. So when we looked at constellations of small satellites, we see that there is some cost sharing between small satellites in the same constellation. So this isn't surprising. In other words, there's a learning curve, right? So, you're building 8 units, you figure a lot of the stuff out with your first unit. Things get easier and easier as you get further on in the assembly line. So with the evolution of new technologies, we wanted to find a way to estimate the costs and evolve how we're estimating it as well. So our research examined approaches to estimating INT costs for small satellites when the hardware base is much lower than the typical traditional hardware spacecraft build. So small sats compared to a lot of the other things we're usually looking at are generally simpler. A lot of the times they might even be commercial off-the-shelf units from industry vendors that are generally less complex and they have cheaper hardware. And so the cost of integrating those multiple identical hardware elements isn't usually accurately reflected. So for this, we decided to come up and develop a CER specifically for predicting small sat INT costs. So how we started is we collected costs and mass data via Cadre. I don't know if everyone in here is familiar with what Cadre is. That's a NASA database that collects costs and technical details on missions of a certain size and from a certain time point forward. So we looked at missions with a total hardware mass, so that includes the payload and the spacecraft, of less than 180 kilograms, and we defined that as our small sat. So that definition is also what's used by NASA, and there's the link below if you want to read more into that. We then normalized all the costs into fiscal year $24 using the NASA New Start Inflation Index. And because the cost data was sort of not uniform, we had to normalize that as well. So we pulled all the INT costs into a single line item. So the INT estimate includes both spacecraft subsystem INT costs and instrument INT costs as well. Those were separated out in the data. We had 5 missions that we were able to collect data on, and 2 of them were single unit missions, but 3 of them were constellations of 5, 8, and 6 spacecraft. So with the objective to develop a parametric CER that calculates INT costs, we considered the following variables. And because we had a limited data set, we focused on one parameter that kind of incorporates many of the other parameters that are on this list as well. So what we decided to go with was the points of integration. And there is some kind of background on using points of integration as an estimating parameter. So there's previous work that's been done at APL looking at INT costs for larger satellites. And that work as well used points of integration. So we kind of leveraged some of the work that was done there in looking at how to use points of integration to estimate INT costs. So the first thing we did was we ran the 5 missions that we had through the this INT CER that was built for larger missions. And what you'll see here is kind of crazy results. An average delta of 306% from cost actuals. We have negative costs in there, and that's, you know, back to what we were saying earlier about the fact that it just isn't, these small satellites are just too small to be estimated in the same way as traditional spacecraft builds are. So thus we should have a specific small sat CER. So based off of industry data, we know that there is INT savings on subsequent units when you're building a constellation. That tends to be about 23%. So we went about this in 2 ways, just kind of to see which would fit better. So we first created a logarithmic model using the total points of integration in the entire constellation. This accounted for cost savings in the model selection. We also did it using a linear model and did a weighted points of integration, and that accounts for savings in the input data. And how you calculate points of integration. So for the total points of integration CER, you count up, so every single spacecraft subsystem is a point of integration, as well as each of the instruments. So for example, if you have 6 subsystems in your spacecraft and 2 instruments, that's 8 points of integration. And if you have a constellation of 4 of those identical units, that's 32 points of integration. For the weighted points of integration model, you do the same calculation, but then we apply that learning factor, that 23% cost savings, to the total points. So similar to above, you would have that 32 times the 77% copy factor, and you're left with 26 points of integration.
All right, so looking at the total points model first, you see we used a logarithmic model since this assumes a learning curve. So looking at total points on the x-axis to predict INT cost on the y, you see an R-squared of 72%, which is pretty strong. Compared to the previous INT work that was done, looking at all size satellites that had a higher R squared, and like all the missions were represented well. You can see here mission 4 and 5 are not as, aren't represented as well as missions 1, 2, and 3. We thought this might be that the previous work that was done, that was an internal APL model, so we had more insight into the cost compared to these are all various NASA missions from different organizations. And while Cadre has a good amount of cost data, sometimes we don't get the same breakout that you would see for internal builds. Next, looking at the weighted points model. So here we have a linear model since the weighted points are accounting for the learning curve. And again, you see a strong R squared here of 71%. So next, testing for heteroscedasticity. We're checking to make sure that there's no pattern in the residuals. And you can see here that there isn't. The trend line would right on the x-axis at 0. So the errors are uncorrelated and distributed normally, and the model is homoscedastic. Next, looking at predictability. So Kathy showed what the average prediction error was for the previous model for these data points, and it was an average of 306%. Now with these two models, with the total points model, you see an average of 7%, and with the weighted points model, an average of 9%. So both have low prediction errors and both are accurately accounting for INT savings. So we have reason to estimate INT costs for small satellites differently than typical missions with larger hardware bases. However, the models that we currently have could be improved with more data. We only have 5 data points right now. Our plan moving forward is continuing to check Cadre as more small satellites are launched and update our models and see how well they continue to do, hopefully. Some suggestions for future research. Some diagnostic tests revealed a distinction between who performed INT, but there were no statistically significant relationships, potentially because we just don't have enough data right now. Also, with the rise of new space organizations getting involved in the development of small sats, there may be an inefficiency inherent in their processes that aren't experienced by more traditional space organizations. So something we'll continue to monitor as well. Next, we started the process of looking at a CER for a RAP factor. So using total points of integration to come up with a RAP factor, looking at INT as a percentage of hardware for constellations of small sats. So within our 5 mission data set, 3 of them were constellations. And so you can see here an R squared of 95%, which is very strong, but since this is only 3 data points, we want to continue to look at this once we get more data. And finally, looking at mass as a predictor of total points of integration and INT costs. So in the upper left, you can see mass predicting total points of integration with an R squared of 76%. And then in the top right, mass predicting INT cost at 81%. And then if you combine these two in the bottom right to have mass predict points of integration and have that then predict INT, you also see an R squared of 81%. So something we plan to continue working on as well. That's it. We'll take any questions.
Yeah, I had one question. How do you guys define small sats, and are you seeing any differences between like a small sat and the CubeSat form factor? Do you have any of those in your data set?
Yes, so I kind of blew past it. So we defined a small satellite as 180 kilograms or smaller. We haven't differentiated between a small satellite and a CubeSat. A CubeSat obviously is going to be more efficient because they can just do a bunch of those because we only have 5 data points. So that's another thing we can add to the future research.
Apologies if we already skipped over this, but I was kind of curious where did you like how did you build the model? Like if I were to do some cost estimation with I am for a project here, where like how would I, like work on building up a model, for cost estimation? Is there like some specific software you guys use or?
So we just used Excel since we were just working with one variable. Here, yeah, with more data points, we would, do more of a regression analysis if we're incorporating more than one variable. But yeah, we were just looking at the one, points of integration variable since we had such a limited data set.
Okay, so this is linear.
Yeah, just linear regression.
Oh, okay.
Any other questions? Thank you, guys.
Thanks.